This is lesson 2.5, and we're going to call it A, because I'm sure there'll be another video. Further applications of right triangles in trigonometry. If you have anything to do with being a pilot or doing anything with navigation on a boat, these guys that do halibut fishing, that kind of thing, have to take this really hard test. I know because I took it like 20 years ago in order to be a halibut captain, and so much of it had to do with being able to navigate using a map and using a compass. And this section has to do with what is called bearing. And what we're going to do is we're going to look at two different ways or methods for expressing bearing. Now, the first method is just using angles. I mean, angles can be anywhere from 0 to 360 degrees. And if we have a compass, and a compass always, and you look at a map, it always points north up at the top of the map or whatever you're using. And you can have a bearing that is 32 degrees. That means that we always start with the due north, and we always go in a clockwise direction. So that's 32 degrees. If I had another measurement that was over here, and I measured that, and that was 229 degrees. So when we're just using one angle, and we are taking it from due north, that is one method as far as solving a problem involving bearing. So we're going to look at the first example, which is example 1, and we're going to use this method here in order to solve this. So let's look at this triangle. So the instructions say that we have a couple radar stations. We have radar station A and we have radar station B. And they are on an east-west line. So this line here goes from east to west. When you're talking about northeast, south, and west, looks like this. So if we've got an east-west line, it's going to be this line right there. And it's going to be horizontal. Alright, so they are 3.7 kilometers away from each other, these radar stations. And let's see, station A detects a plane at C. So A detects a plane up here at point C. And the bearing on that is 61 degrees. So again, we're talking 1 degree angle, and it's from the north, counterclockwise 61 degrees. And we draw a line. We don't know where along this line C is, but we do know that it's along this line at 61 degrees. Alright, station B also detects the same plane on a bearing of 331, all the way around to 331. So we can go up to 360 degrees and we'd be all the way back to where we started. So they draw a line at 331, so all the way around to 331 they draw a line. Where these two lines cross is where the airplane is. So if you get a mayday from an airplane and you don't know exactly where it is, they can, with radar, determine this angle and this angle, draw the two lines together, and find out where that plane is. So, what they're asking us to do here is find the distance from A to C. They want to know where that airplane is along this line. And if they know where that airplane is along that line, they can take a map and know exactly where that airplane either crashed or is at. So we're looking for this distance. Notice this is a 90-degree angle, so we have a right triangle, which means we can use our trig functions in order to solve for this. So let's go ahead and do that. One of the things that really helps is if you've got a drawing of what you're going to be solving here. So let's go and look and see what we've got. We know this is 61 because this was 331, and we don't necessarily have to go by that, except we know this angle here, or this line here, goes to C. So we know that's 90, we know that's 61, and in order to get here is 29, to get to a 90-degree angle because we said this was on the east-west line, and east-west, north-south form a 90-degree angle. So if this is 61, this is 29. If this is 90, 90 plus 29, we add another 61 and we get 180 degrees in a triangle, or these two angles have to add up to 90. So that's how we got the 61 degrees there. Alright, so what we're looking for is the length of angle B. So from this angle we are looking for the adjacent side. So what trig functions do we know that have to do with the adjacent side? Well, we know tangent of theta is opposite over adjacent, and we know cosine of theta equals adjacent over hypotenuse. Alright, let's continue looking at what information we have. We have the angle. So we've got this point, this here, tangent of 29, cosine of 29. So out of the 1, 2, 3 variables that we have this one here. From this angle, do we have the opposite? No, we do not have the opposite, nor do we have the adjacent. All we have is the angle. So we can't use our tangent. That's not going to be something that we have an opportunity to use because we're still missing 2 of the 3 unknowns. We can only be missing 1 of the 2 unknowns. So cosine, what do we have? We have the 29 degrees. So we have the cosine of 29 degrees, just like we did with the tangent. We don't know the adjacent, just like in the tangent one, but we do know the hypotenuse is 3.7. This is the hypotenuse because it's across from the right angle. So therefore, we can solve this because we only have 1 unknown here. So if you remember from past, I said if we have the unknown on the top, we just multiply these 2 together, and that'll give us our B. So B equals the cosine of 29 degrees times 3.7 degrees. So therefore our B equals 3.2 kilometers. So the distance from A to C is 3.2 kilometers. A second method for expressing bearing has to do with the north-south line. So I'm going to use this as my north-south line. It's always up and down. And what we do is we always use an acute angle to show direction. So in the other one, I had my north-south line and my east-west line, and I started at north, and I could have an angle anywhere around here. So let's say I said it was 230 degrees. Well, that would be 230 degrees. In this new way of doing it, or the second way of doing bearing, our angle will never be greater than, or it will always be an angle less than 90 degrees. Because what we do is we just name the angle differently. So if I were to name this angle right here, this 42 degree angle, let me get rid of this here, and looking at this picture, I would call that north, which means, all right, so we're always starting right here. So here's our line, our north, south, east, west line. So this is my west, east, south. Okay, we're always starting here. 42 degrees. In order to get 42 degrees here, I had to be on the north line, not the south line. The south line would be below the line, but the north line. And I would not only be on that north line, let's get rid of all this stuff first. I would also be going 42 degrees to the right. 42 degrees right means east. So I'm on the north line above the east-west line, and I'm 42 degrees to the right, which is east. If I were on the north line going the other way, like this one over here, I would be north line 52 degrees left, or in the west direction. So I would get this line by going north 52 degrees west. That's the same as if I were here going all the way around and getting 308 degrees. But it's just a different way of saying it, because then it keeps all of your angles less than 90 degrees, And it also then gives you the opportunity to use north 52 degrees west. Now let's say that I'm on the south line. Let's say that this is my east-west line and I'm going below it. If I'm below it, I would say I am on the south line and I'm 31 degrees to the right of the south line, or 31 degrees east. So I would say south, 31 degrees east. South line, 31 degrees east. Over here, same thing. South line, 40 degrees to the left, or 40 degrees to the right. Or I'm sorry, west. So that's the way you say these. This is, out of all the two different methods of determining bearing, this is the one that's the most used. If you look at a map of your neighborhood and it has your lines for your property, it will use these kind of degrees when it measures what kind of direction your property lines are going, that kind of thing. So good to know that one. All right, so let's get this smaller and let's look at this example here. Kind of move this over here a little bit. And this is example number 2. All right, so let me use my laser pointer. The bearing from A to C, from A to C, is south line, 52 degrees east. So that gives me this line right there. Okay, so all that does, that 52 degrees, just tells me where that line is going to be from the north-south line. So then I just draw this line at 52 degrees and I have AC. The bearing from A to B is north line, because A is the center, it's the point, it's where your east-west and north-south line are. Whoops, that doesn't really show my very good east-west line, does it? Okay, so that line is where we're starting. Okay, so we are north 84 degrees west, or east. The bearing from B to C, okay, is south 38 degrees west. And then we can draw that line. So that gives us a chance to draw this line, and this line. So a plane is flying at 250 miles per hour. He takes 2.5 hours to go from the here to here. And they're interested in us finding the distance from, see if I can get my pen to work right. They want us to find the distance from A to C. So that's what we're going to look for, is the distance from here to here. Okay, so first of all, we need to figure out why in the world they told us that if a plane takes off from here and goes to here, he's flying 250 miles an hour. It takes 2.5 hours to get there. What does that have to do with finding the distance from A to C? The whole airplane thing just didn't make sense to me when I first looked at it until I realized that that would give me a length of this line. If it takes 250 miles to go 2.4 or 2.4 hours to go 250 miles, if I multiply those, then that will give me my distance from A to B, which is 600 miles. So that's the only reason they gave you that information, is in order to get the length of line C. Because one of the things that's necessary to know about trig, we can't find the distance from A to C unless we know one of the other distances of this triangle. Just because we're given a whole bunch of angles doesn't mean we're going to be able to find a distance. We have to have one other length in the triangle in order to find the other length. So just something to remember, that they're going to have to tell you that bit of information. So now that we have that length being 600 miles an hour, and we know that that's the hypotenuse, because notice our little angle here, see the pointy side? It points to its opposite side, or it always points to the hypotenuse. So I know that my hypotenuse is 600 miles. Okay, so we're looking for the length of AC. So if we were to use this angle right here, 44 degrees, which we determined just from the information they gave us from here all the way to here is 180. They told us 84. They told us 52. 84 and 52 do not add up to 180, so there must be another number in between here that would give us 180 when we add them up, and that's the 44 degree angle. So let's see. We're looking for B, and B is an adjacent angle. So again, we're looking for a trig function that has adjacent. So the tangent of 44 degrees equals adjacent over opposite. And we don't know the length of that line there. So tangent isn't going to work. So let's look and see what our other options are here. We can try cosine, because cosine also has adjacent in it. So cosine of 44 degrees is cosine is adjacent over hypotenuse, which is 600. So that one works. So then I do my manipulation of my numbers, and I get 600 times cosine of 44 degrees. And I end up getting 430. Now, I could have used this, so let's use black here. I could have used this over here and used the sine of 46 degrees, because that equals opposite over hypotenuse, which is B over 600. And then I could have multiplied 600 times the sine of 46 degrees and gotten my 430 miles as well. So either way works fine. So that is 2.5a. 2.5b will continue on.